In this presentation, we'll talk about the importance of linear phase on time domain measurements. In particular, filters that have linear phase impart equal delay to all frequencies in the passband for spectrally rich signals. A filter or transfer function that has nonlinear phase will impart different delays to frequencies across the passband of the filter. If you have, again, an input signal that's spectrally rich, has lots of frequency content, you will see different delays to those frequencies that comprise a signal across the passband. Those different delays will produce what we call waveform distortion. A measurement of how good a filter's linear phase property is called group delay. And group delay is defined as a negative derivative of the phase with respect to frequency. So if a filter has linear phase, then it stands to reason that the derivative of a filter with linear phase is a constant. Hence, we refer to filters with constant group delay. That's equivalent to saying that the filter has linear phase. The Bessel filter, which you may have studied, is a well-known filter in the family of all-pole filters, in that it is designed to maximize or optimize the phase linearity for a given order or given number of poles. The Bessel has almost perfect phase linearity in the passband, and in exchange for that, the amplitude response is quite broadly rounded when compared to a Butterworth or a maximally flat elliptic filter. Precision Filters has developed a transfer function that we call the pulse mode or pulse mode linear phase filters. The pulse mode filters have amplitude response similar to their Bessel counterparts, and the passband, in fact, is nearly identical. But in studying the top chart on the left, you can see that the transition rate of the LP8P pulse mode filter is much more abrupt than its 8-pole Bessel counterpart. The pulse mode filter is down 80 dB at about 3.5 times the program cutoff frequency, while the 8-pole Bessel is down 80 dB at 6 times. So much more selective, abrupt transition region. So back to the notion of group delay. If we look at the group delay for the LP8F flat mode filter and the LP8P pulse mode filter, Precision Filters characteristics, we can see with the red arrow that the group delay of the LP8F is not constant as we go through the passband. The passband here is defined from 0 to 1 in normalized frequency. So the fact that the group delay is not constant implies that this filter does not have linear phase, and it will not impart the same delay to all frequencies in the passband of the filter, i.e. it's a poor choice when we're analyzing waveforms in the time domain, and wave shape reproduction is important. Looking at the green arrow, that's pointing to the group delay of the pulse mode filter, and we can see in the passband from 0 to 1 that the group delay is a constant. This filter has linear phase. It will impart the same time delay, input to output, to all frequencies in the passband of the filter, and it will preserve wave shapes in the time domain. A term we refer to as phase distortion is a deviation of the actual phase versus frequency curve when compared to an ideal characteristic for linear phase. And here we have two plots. The one on the left is the phase distortion of the elliptic flat mode filter. Its phase response, again, is nonlinear across the passband, and we can see the phase distortion curve grows from minimal phase distortion up to about half the cutoff frequency. Maybe we have 5 degrees at half the cutoff frequency, and then it starts to get significant where at the cutoff frequency at 1, we've got about 100 degrees of phase distortion. On the right, we're looking at the pulse mode, LP8P, and it has linear phase, and the phase distortion curve is less than 0.05 degrees across the passband. So excellent phase linearity for the pulse mode characteristic. We can do a couple experiments to demonstrate why linear phase is important. And what we're going to do is take a pulse mode filter with a cutoff set at 3 Hertz, and we're going to put in a hypothetical waveform that's comprised of the first 2 harmonics of a square wave, the fundamental and third harmonic. And we'll look at the output on an oscilloscope. If we do that, we see that the input and output are shifted in time with respect to each other. The time shift is equal to the phase delay of the filter. But we can see also that the wave shapes of these two the input and the output have been maintained thanks to the constant group delay property of the pulse mode filter. Now we'll do the same experiment using an 8-pole elliptic filter set at 3 Hertz. This has a very, very flat passband but nonlinear phase. And the result of this experiment shows that the output doesn't look very much like the input. And the reason is that the fundamental and third harmonics of our hypothetical waveform received different input to output time delays as they passed through the filter, and superposition of those two waveforms at the output shows a waveform that is distorted, that does not look like what we put in. So given that we have a measurement system and we want to faithfully reproduce a wave shape in the time domain, what criteria should we use in setting up the transfer function of our measurement system? Well, there's 2 criteria that we've talked about. One would be that the amplitude response of the filter be flat enough so as not to impart attenuation to the frequency content of the waveform we're trying to measure. And the second criteria would be that the frequency content of the waveform we're trying to measure lie in the linear phase region of the transfer function of our measurement system, so as not to cause waveform distortion. So Pat Walter and Chuck Wright, they're 2 test and measurement gurus, and they lecture throughout the country and throughout the world. And they've proposed a criteria of 5% amplitude flatness and 5 degrees phase linearity be generally sufficient for wave shape to be properly preserved. So we'll stick with that criteria as a means to set up our transfer function. So let's start with an example. Suppose we have a measurement system that has a 2-pole AC coupled input at 10 Hertz, meaning it's going to block frequency content in our input waveform at 10 Hertz and below. And then we've got an 8-pole flat mode LP8F precision filter, low pass filter, and its cutoff is set to 25 kilohertz. We're trying to measure shock, and we want a flat bandwidth to within 5% from 100 Hertz to 10 kilohertz. And we want phase linearity to within 5 degrees from 100 Hertz to 10 kilohertz. The question is, will the system meet this requirement? So we plot the amplitude response of our system, and we look at the 0.5 dB or 5% flatness region, and we find that the 2-pole AC coupled high-pass network is 5% down at 18 Hertz, and the LP8F low-pass filter is 5% down at 22.5 kilohertz. So from 100 Hertz to 10K, we're great. We're well within the 5% criteria that we were looking for. Let's look at the phase response. This is the phase response of the measurement system. And to determine the phase linearity, we want to look at the phase distortion curve. So this phase distortion curve is plotted with respect to the zero frequency phase slope of the 8-pole low-pass filter. So we've plotted the phase distortion, and we see that at 100 Hertz we've got more than 5 degrees, our criteria. So right away we know that this system is not going to work. In fact, its 5-degree linearity span is 160 Hertz to 11.5 K. So we make it on the upper end, 10K being our requirement, but at the lower end we're not making it. So the answer is no, we can't do it with this system. And what could we do? Well, to reduce the phase nonlinearity at the low end, we can reduce the frequency of the 2-pole high-pass filter if our system's programmable, or we can reduce the order of the high-pass filter from 2 poles to 1 pole, which will reduce the amount of phase shift we have down there. So we can take measure against this if we have a programmable system, and PFI sells programmable systems for this reason. If it's not programmable, then you're not going to be able to meet the criteria. You're going to have to relax the criteria. In this presentation, we talked about the importance that linear phase has on valid wave shape reproduction. We also introduced some criteria for setting up a measurement system transfer function for valid wave shape reproduction. Thank you for listening.